Hi everyone, welcome to moscan. So in today's video, we have been given one question which is based on the differential amplifier. You can see here one differential amplifier is drawn here. In this question, it is given that the one input V in 1 for this MOS M4 is given equal to VDD by 2. That means this input is constant for this differential amplifier, whereas the other input of this differential amplifier, which is denoted by V into, it is time varying input. So the graph of this V into is given here. It is changing, its value is changing from 0 to VDD, and VDD is the maximum supply of this differential amplifier. So we have to draw the output waveform for three nodes. We need to plot V out with respect to time. We need to plot this VB voltage, which is the drain of the tail current source, how it will vary with respect to time if this input V into is varying. And also we need to plot the current I2 flowing from this MOS M1 with respect to time. Also in this question it is given that this current from this tail current source is equal to IDC, because these M5 and M6 are forming a current mirror and the aspect ratio is 1:1. So whatever current is flowing from M5, the same amount of current is flowing to this MOS M6 also. So the current through M6 is IDC. So these all information is given in this question, and then we need to plot the voltages for V out, VB and the current for I2 with respect to time. So let's start solving this question. So we will start by analyzing three conditions. What will happen when input is 0, then what will happen near around VDD by 2 or equal to VDD by 2, and what will happen after that when input is at VDD. So by plotting these three conditions, we can end up having the output waveform. So let's start solving this question. What will happen when input is equal to 0? That means V into is sitting at 0 volt. So it is very obvious that if the gate voltage of any NMOS is sitting at 0, that means that NMOS will be in turned off condition. That means this V into, if this V into is 0, this MOS M3 will be in cutoff mode. There won't be any current flowing from MOS M1 either. So as we have discussed, M6 is having current equal to IDC, and since this MOS M4 is on, because V1 is given as VDD by 2, so whatever current M6 is supposed to have, the whole current will flow from M2 to M4 and then from M6. So IDC will start flowing from M2, it will flow to M4 and then it will go to M6. So there won't be any current in I2, but yeah, from M2 to M4 to M6, there will be a current, and the value of that current will be equal to IDC. So if I try to plot the waveform of I2 with respect to varying voltage of V into, so when input is 0, my current, which is I2, that will also be 0. This is the first observation which we have. Now let's also try to understand how V out and VB will behave in that condition. So when my V into is 0, as I mentioned, there won't be any current from MOS M1, that means I2 is 0. But this MOS M1 will be turned on in this condition, because if you see, there is a VGS for this PMOS. Source potential is VDD and gate potential will have certain value, because there is a current from VDD to M6 to ground. That means there will be some drop across this diode connected MOS, and so its source will define the gate potential. So this MOS M1 will be on, but there won't be any current flowing through this, and this can only happen if the VDS across this MOS M1 is 0, right? There is a condition for MOSFET. If VDS is greater than or equal to VGS minus VTH, it will be in saturation and current will flow. So right now VGS minus VTH is getting justified, but VDS is 0 for this MOS. In that condition, there won't be any current flow, but MOS will be on. So that means V out will be sitting at VDD when V into is sitting at 0 potential. So let's try to draw that waveform also. We will combine V out and VB waveform in one waveform. So if voltage V into is sitting at 0, at that time, if I have to plot V out, that will be sitting at VDD value. So this is my V out, and it is equal to VDD right now, here. What will happen to VB? Let's try to understand that also. Since MOS M4 is on, so if I have to write VB potential, its VB potential can be written by delta VGS of this MOS M4 would be equal to VGS4 minus VT. We are assuming that VDD voltage is quite high, and these all MOSFETs are having a good overhead voltages, and this M6 is operating in saturation condition. This is already assumed. So if I have to write VGS4, that will be equal to delta VGS4 plus VTH. Right. We know VGS can be written by VG minus VS, and we are trying to find this VB potential which is source for this MOS M4. So if I replace this VB with VS with VB, so VB will be equal to VG minus VGS, and VGS4 we already have figured out this value. So that means VB will be equal to VG is VDD by 2, V in 1 is given to us, that is VDD by 2, minus VGS4 is nothing but this value delta VGS4 plus VT. So that means VB voltage will be slightly lesser than what V in 1 is sitting at. So if V in 1 is sitting at, let's say if this is VDD, this half mark is VDD, so our VS will be somewhat less than delta VGS plus VT factor from VDD. So let's say VS will be sitting somewhere at this value when input is equal to 0. Now let's analyze the other case when input is sitting at VDD by 2. But before that, if you observe this particular condition where we have analyzed V in equal to 0 case, you see VB value is somewhat VDD by 2 minus some delta VGS plus VT factor. That means unless V in 2 will not reach VB plus VT, this MOS M3 will never get turned on, and there won't be any change in I2 and V out either. So that means once this V in 2 will start reaching at VB plus VT, some current will start flowing from this M4, and when V in by 2 will sit at VDD by 2, at that time, since both of the structure will be symmetrical, so current will be equally divided in both the MOSes. That means I2 and I1 will become half of IDC. So if I have to draw the waveform, so let's say if this is VDD by 2 for me, so before that, slightly before that, that means when this V in 2 is VB plus VT, I can write this as VB plus VT also. At that time, current will start increasing, and at VDD by 2, it will reach exactly IDC by 2, and before that it will start rising as our V in 2 will change. So this is how my current waveform will look like for I2 when my input V in 2 is equal to VDD by 2, or M3 has started to turn. Now let's talk about V out and VB also. Since V in 2 is sitting at VDD by 2, that means current from M4 has reduced. Earlier it was completely IDC, but now since V in 2 is sitting at VDD by 2, current has become half here. Now if I talk about VB voltage, earlier when complete current was flowing through MOS M4, VB was sitting at VDD by 2 minus delta VGS plus VT. Now since current is half, so VGS value will also decrease here. If VGS is decreasing, that means VB will go up. So when V in 2 is equal to VDD by 2, my VB voltage will move up. So if I have to draw VB here, initially it was sitting at somewhat this value. Let's call this as VDD by 2. So earlier it was sitting somewhat lesser than VDD by 2. Now once our input is sitting at VDD by 2, it will go up. Whether VB will be equal to VDD by 2 in that case, that we can't say, because V in 1 and V in 2 both are VDD by 2 now, so VB will definitely be lesser than that. Now if I talk about V out, earlier when current was 0, V out was equal to VDD, but when current has started to flow from MOS M3 also, So this Vout will be equal to VDD minus one threshold drop across this MOS M1. So Vout will drop, and it will drop at this value where you can consider it as equal to VDD minus delta VGS drop of this MOS M1. Now let's talk about the third case when my input 2 is sitting at VDD. When input 2 is sitting at VDD, if Vin2 is going to VDD, so one can simply think since there is a lot of VGS, this Vout will go to 0, but that's not possible because if you see here, Vin1 is always sitting at VDD by 2, and this MOS M2 and M1 is forming a current mirror. That means whatever current is flowing from MOS M2, the same amount of current has to flow from MOS M1. And the same amount of current will flow from M4 and M3 also. That means the current will always be equal, and that can only be possible if you see here VGS is very high. For this MOS M3 VGS is different, and for MOS M4 VGS is different, but we are saying the current will be same. That is only possible when there is a change in the drain to source voltage of MOS M4 and MOS M3. So that means we were assuming that MOS M4 was working in saturation because this Vin1 was sitting at VDD by 2 always, but since this Vin2 is going to VDD potential, this VGS will be very high, but VDS will become so low that it will go into the triode region, a linear mode of region, and the current will eventually become equal to what current is flowing from MOS M2 to M4. So that means my current will still be equal to IDC by 2 when my Vin2 is sitting at VDD. So if I have to plot the current waveform, it will be sitting at IDC by 2 even when my input is at VDD. The current is not changing. It was 0 till VB plus VT, then it started to rise, and from VDD by 2 onwards it is always at IDC by 2. So this is the current I2 waveform. Now since current is same, again my VB potential will not change. VB potential will be still the same what we were getting at VDD by 2, so it will follow the same. It will still not touch VDD by 2, but if I talk about Vout, now since Vin2 is having a lot of Vin2 is having a higher VGS, my Vout will eventually drop further and it will come closer to the equal to VB. Again, if you try to analyze this carefully, Vout minus VB will be positive. It cannot be 0 because that's the VDS for MOS M3. Vout minus VB is VDS for MOS M3, and it has to be a positive value. If this becomes 0 or negative, that means there won't be any current. And as we have understood, even though Vin2 is sitting at VDD, current has to be equal. Whatever current is flowing from left branch, the similar amount of current should flow from right branch. That means this delta will be positive, right? So although Vout will be quite less because the Vin2 is sitting at VDD value, but it will still be higher than VB potential. So whatever VB potential we are getting, Vout will drop. If you compare Vout at VDD by 2, whatever value we are getting, we will get lesser than that when my Vin2 is sitting at VDD, but it will still be more than what VB is sitting at. So Vout will drop, but it will be still higher than VB potential. So this is at VDD. So these are the three waveforms which were asked in this question. One was current I2, which we have drawn. It was 0 initially, then from VB plus VT, it started to rise. At VDD by 2, it is exactly equal to IDC by 2, and then it is same throughout the voltage change. And if I talk about Vout, it was initially at VDD. This you can consider at VDD voltage. Then once some current start to flow from MOS M3, it started to decrease. At VDD by 2, it is VDD minus VGS of MOS M1, and then after that, when my input 2 is changing from VDD by 2 to VDD, Vout will drop further, but it will be slightly higher than what VB is sitting at. Now if we talk about VB, initially it was having certain potential which was equal to VDD by 2 minus of this VGS of MOS M1. When my input 2 reached at VDD by 2, at that time VB was slightly higher because current was reduced from this MOS M4 earlier whole I current was flowing. Now it is high by 2. Since current was reduced, so VGS was reduced and VB was slightly increased. So that's what we have shown here. And now, even though my V into is sitting at VDD, but still the current from left and right branch is same. That is, VB will be unchanged. So VB is still same, but less than VDD by 2. So this is all the three waveforms which were asked in this question. I hope you got to learn something new from this question. If you found this video useful, please share with your friends. And if you aren't subscribed to our channel, please do subscribe.